Now we are going to our next theorem. Let H be a Hilbert space. A is a bounded linear operator on H. Then K is in sigma E if and only if K bar is in sigma A star. That is, for any bounded linear operator E, when K is the spectral value, then K bar is the spectral value of its adjoint. That is the statement. When K is the sigma A, that is K is the spectral value of E, then K bar is the spectral value of A star. Reversely, if K bar is the spectral value of A star, then K be the spectral value of E. How to prove this one? So the proof is immediate. Why? Because let K fall in K, choose a scalar, K is in K. Then let A minus K is in sigma A means A minus K is not inverted. So let K is outside of sigma A. K is outside of sigma A means A minus Ki is inverted. So A minus K is inverted. A minus K is invertible means A minus Ki. This means A minus Ki or inverse exists and which should be present in BLH, which is a bounded linear operator. Okay. Now, what is A minus Ki star? We know A minus Ki star equals, it is A star minus K star. K star means K bar. It is K bar of phi. So A minus Ki star equals A star minus K bar I. So we know that when A is invertible, A star is invertible, or A is exist, then we know that that's a well-known theorem, or it's a proved theorem. The theorem states that when this is A minus Ki star equals A star minus K bar I. So when A minus Ki is invertible, yes, A bar minus or A minus Ki star is also invertible. That means A star minus K bar I is invertible. This is invertible means this K bar is strictly outside of which one? K bar is outside of sigma A star. When K is outside of sigma A, that should imply K bar is outside of sigma A star. So the reverse inclusion is also called. That means K fall in sigma A if and only if K bar fall in sigma A star. So what is actually sigma A star? Here sigma A star equals set of all K bar fall in K. So this sigma A star can be rewritten as sigma A star equals set of all K fall in K. Set of all K bar fall in K such that K fall in sigma A. So this sigma A star can be redefined as in this way. Sigma A star equals set of all K bar fall in K such that K fall in sigma of E. So this is our result. When K is outside of sigma A minus Ki inverse exists and is in BLH. But A minus Ki star is A bar minus K bar I. Since A minus Ki is invertible, surely A star minus K bar I is also invertible. So that means K bar is outside of sigma A star. So clearly we can say that, then we can conclude that K is fall in sigma A if and only if K bar is fall in sigma A star. So this is our first theorem. Okay. Again, we are going to another argument. Sigma E of A, when H be a Hilbert space and A is in BLH, then sigma E of A is a part of sigma A of A. Again, this is an already proved result. And sigma A equals sigma A of A union set of all K such that K bar fall in sigma E of A star. So this is our next theorem. If H be a Hilbert space, A is in BLH, and then sigma E of A is a part of sigma A of A, and sigma A equals sigma A of A union set of all K with K bar fall in sigma E of A star. How to prove this one? So far, its proof is let k is an eigenvalue of A. Let k fall in sigma E of A. K is an eigenvalue of A means there exists some non-zero x fall in H with we know that there exists some non-zero x fall in H with Ax equals Kx with norm x equals 1. Okay, K is in sigma E of A. K is an eigenvalue of E. So this x, what is this non-zero x? That is known as the corresponding eigenvector. There is an eigenvector corresponding to this eigenvalue having norm 1. Agree? Now let xn equals x. Xn equals x means what is norm xn? Surely this norm xn equals norm x, but norm x is 1, so finally norm xn is also 1. Enough. So what is axn minus kxn? Now axn minus kxn equals, it is xn means x, it is ax minus kx, but ax equals kx, so ax minus kx equals 0. This means axn minus kxn equals 0. Axn minus kxn equals 0 means it is a minus k of xn. A minus k of xn goes to 0 with there is some non-zero or there exists some xn falling h with norm xn equals 1. So that means a minus k of xn goes to 0 means what is this k? That means k is an approximate eigenvalue of E, k falling sigma E of A. Okay, so clearly this k, when k falling sigma E of A, that means so that same k falling sigma E of A, so the first part is finished, that is sigma E of A is a part of sigma A of A. Agree? Okay. Now come to the second part. Come to that. Now we have to show that the sigma A equals sigma A of A union set of all k with k bar falling sigma E of A star. How to prove that one? So for assume k is outside of sigma A. Assume k outside of sigma A. K outside of sigma A means A minus k is invertible. That means again more precisely it is A minus k inverse exists and which should be falling BLH. So this is the invertibility of A minus k. Okay. Now what is norm x? Now starting from norm x. Norm, we know that norm x equals norm A minus k into A minus k inverse into A minus k of x. A minus k inverse into A minus k is that's identity. So means which is less than or equals, we know that norm A B less than or equals norm A into norm B, that is norm A minus k inverse into norm A minus k of x. So bring this or put this norm A minus k inverse is some beta, some 1 by beta, or put up beta equals some 1 by norm A minus k inverse. So means norm 1 by norm A minus k inverse into norm x. This means 1 by norm A minus ki inverse into norm x less than or equals norm A minus k of x. This is taken as beta. That means some beta norm x less than or equals norm A minus k of x for some beta greater than 0. This means A minus k is bounded below. A minus k is, this means A minus k is bounded below. A minus k is bounded below means surely this k is strictly outside of sigma A of A. When k is outside of sigma A, then clearly the same k is outside of sigma A of A. This means sigma A of A is a part of sigma E. Okay, so here we can conclude that when k is outside of sigma A, that k is outside of sigma A of A, So we can conclude the sigma A of A is nothing but a part of sigma A. Okay. Now again, consider this result. We got this one. Sigma A of A is a part of sigma A. Now again, if K bar is outside of, if K bar which is outside of sigma E of A star, K bar is outside of sigma E of A star. So but we know that sigma E of A star is a part of sigma A star. That's we already proved. Sigma E of A is a part of sigma A. If you replace A by A star, so sigma E of A star is a part of sigma A star. So K bar is outside of, if possible, K bar is outside of sigma E of A star. Sorry, not outside, sorry. K bar is, suppose K bar presents in sigma E of A star. When K bar presents in sigma E of A star, that K bar should present in where? K bar presents in sigma A star. Why? Because of this argument. K bar presents in sigma A star. K bar presents in sigma A star means this K presents in sigma A. Why? Because of our previous results. Why? K fall in sigma A. We know that the previous result says that K fall in sigma A if and only if K bar fall in sigma A star. So when K bar fall in sigma A star, that means K fall in sigma A. Okay. Thus, this means set of all K bar, set of all K such that K bar fall in sigma A star, or sorry, sigma E of A star. Sigma E of A star is a part of sigma E. Set of K bar fall in sigma E of A star, but sigma E of A star is a part of sigma A star. So, but when K bar fall in sigma A star, that means K fall in sigma A. So finally, this can, if you combine this, then we conclude set of all K with K bar fall in sigma E of A star is a part of sigma E. Okay, so this is our first conclusion. Sigma A of A is a part of sigma A. Again, set of all K with the K bar fall in sigma E of A star is a part of sigma A. Okay, so thus sigma A of A union this one is a part of sigma A. Thus combines these two. This is 1, this is 2. So combines 1 and 2 combinedly gives 1 and 2 combinedly gives sigma A of A union set of all K with a K bar fall in sigma E of A star is a part of sigma E. Okay, so the first inclusion is proved. Now for the reverse inclusion, for reversing, assume K outside of sigma A of A. K is outside of sigma A of A, and K bar is outside of sigma E of S. Okay. Assume K is outside of sigma A of A and K bar is outside of sigma E of S. What happens here? K is outside of sigma A of A means A minus K is bounded below. Clear? This, consider only this one first. That means this A minus K is bounded below. A minus K is bounded below. So K bar is outside of sigma E of A star means it is A star minus K bar I is injected. This is one is injected by definition. Okay. We know when A is injective, what happens here? We know that when A is injective, then a range of A star is dense in H. That's a well-known result. Similarly, when A star is injective, range of A is dense in H. Okay. So clearly, as by that argument, A star minus K bar I is injective means if you replace, so it is range of A minus K is dense in H. Range of A minus K is closed and is dense, closed and is dense in H. Okay, range of A minus K is closed and is dense in H. Range of A minus K is closed and is dense in H means what is A minus Ki? That means A minus K is surjective, means it is one. Okay, range of A minus K is dense in H means A minus K is onto. So listen, here A minus K is onto. That's our next result. A minus Ki is onto, means it is surjective. Now again, consider A minus K is onto, but K is outside of which one? We know, we assume K is outside of sigma A, means A minus K is bounded below. That means there exists some beta greater than 0 such that beta norm x less than or equals norm A minus K of x with the norm x for x of all in h. Okay. So this means this A minus K is 1. Okay, A minus K is 1. So A minus K is 1, 1, A minus K is 1, 2. That means A minus Ki is bijective. A minus K is bijective means its inverse exists. So you can define this A minus Ki inverse from H to H. Okay, so but we know that this A minus Ki inverse is also A minus Ki is linear, A minus Ki inverse is also linear. Now to show that this A minus, in order to show this A minus Ki is invertible, first we show this A minus Ki inverse exists. Next we have to show that this A minus Ki inverse fall in BLS. So for that, the linearity of A minus Ki inverse is preserved here. Now remains to show this A minus Ki inverse is bounded. How? If y fall in H, let x equals A minus Ki inverse is defined from where to where? H to H. So for each y fall in H, put x equals, there exists some x of all in H, such that this y equals, so x equals A minus Ki inverse of y. Okay, why? Because it is, consider this map, this is on A minus Ki inverse defined from H to H, which is linear. Then for there exists some y fall in H, so with then norm A minus, so A minus Ki inverse of y equals x for some x of all in H. So thus beta into norm A minus Ki inverse of y, beta into norm A minus Ki inverse of y less than or equals norm A minus Ki, that is x equals this one. So beta norm x, this one, consider this one. This relation becomes, so this becomes beta norm x less than or equals norm A minus Ki of x, but x is defined as this one. So beta into norm A minus Ki inverse of y less than or equals A minus Ki into A minus Ki inverse of y. Okay, that means this is equals to norm y. So identity. So beta into norm A minus Ki inverse less than or equals norm y. That means norm A minus Ki inverse less than or equals 1 by beta. Beta into norm A minus Ki inverse of y less than or equals norm y. So norm A minus Ki inverse less than or equals 1 by beta. That means A minus Ki inverse is bounded, but it is linear, hence it is in BLH. Therefore, A minus Ki inverse is in BLH and is exists. That means K is outside of sigma A. Sorry, that means yes, K is outside of sigma A. So when K is outside of sigma A of A, K is outside of sigma A. When, so that the reverse inversion is also finished there. Hence, sigma A equals sigma A of A union set of for K with the K bar for sigma A of S. Agree.